Hey folks, we're here for our second lesson. We're actually going to kind of just do part two to this lesson. This should all sound familiar, again, stuff that you've done before in Algebra 1. Nothing fancy here, but just trying to kind of stir the brain a little bit at the start of the school year, and so that's why we're kind of in the middle of the unit here. We're going to solve systems by substitution and elimination. Again, our goal is to provide a variety of tools for solving systems, and we explored graphing last time, which was sort of rehashing a lot of skills. How do we graph lines? What are vertical lines versus horizontal lines versus y equals mx plus b lines? How do we handle that? How do we create our table of values, plot the points, etc.? And today we're going to focus on solving systems of equations using substitution and elimination. So not the next lesson, that's actually today, it's happening now. And so we had this information from last time where sometimes we would have lines that would intersect and it would give us a solution in x comma y. Sometimes they would coincide, and we call that a dependent situation where they were the same equation, just maybe written different ways. Or parallel lines where they had the same m value but a different b value in the y equals mx plus b equation, and we call that an inconsistent system. Well, as we're solving algebraically, we should get an x comma y answer. X equals this and y equals that. So the solution is this point x comma y. When we're solving algebraically using elimination or substitution, we may have a case where we end up with just a true statement like 0 equals 0 or 5 equals 5. And that's great if that happens. It just means that there's not an x comma y solution. There's infinitely many solutions. It's dependent. Likewise, if we are solving using elimination or substitution and we write a false equation at the end of our work, like 0 equals 3 or 10 equals negative 2, like that's not a true statement, that's a false statement. Therefore, there would be no solution. There's no values of x or y that would make this system actually work. So that would be our inconsistent system. Keep this bottom part in mind as we work through some of our examples today. So here's kind of a step-by-step approach for how we solve a system of equations using substitution. Keep this handy so we can reference it, you can do the things. Now, this again is not new, this is stuff that you've done before, but maybe have it down so you can reference that. We're going to solve by substitution by getting one of the variables and one of the equations by itself. Sometimes it's y, sometimes it's easier to get x by itself, sometimes it doesn't matter, it's hard both ways, it's easy both ways, doesn't matter. But once we learn what that variable equals, it might equal an expression instead of a number, we're going to substitute that whole expression into the other equation and then solve for that variable that we have remaining. This will give us a number answer for that variable, which we can then use to find the other number answer for the other variable, so we can write our x comma y solution. So let's go ahead and do a couple of these. This is a little bit new for me as far as the time it's going to take for us to do these. Folks are funny because they're like, I want the video short, but I want a lot of examples. It's like, well, I don't know what to tell you. So we're going to do a ton of examples today, but the goal here is to make sure that we can do the basic things. So if I'm going to do substitution, it would be really easy for me to get x by itself in this first equation. So I'm going to take x equals 12 minus 3y, right? If I subtract 3y from both sides, I get this. And since I know that negative 2x and 4y is equal to 9, that means that I can substitute what x equals in place of the x in the other equation. So now I have negative 2x and 4y is equal to 9. This is going to solve for y, which is a little bit strange, but I solve for x. That means I'm going to be able to figure out what y is. Yes, I have to do my Algebra 1 correctly here. I trust that you are fully capable of that, and if not, then let's have a conversation and figure out if we're in the right spot. But I'm going to combine my like terms. I'm going to solve my equation, and we're going to work in that way. I add these up, and I get 33. I'm going to divide both sides by 10 to find out that y is equal to 3.3. All right, now, once I know what y equals, I can use this value in either equation to figure out what x is. Now, it would be easiest to just plug it in over here, or where x is already by itself over there, if I can trust my work there. So I'm going to do that. I'm going to put it back into this equation that I created at the first spot to say that x equals 12 minus 3 times whatever y equals, which is 3.3. So now I have x equals 12 minus 9.9, so x equals 2.1. All right, so that's what x is, that's what y is. The solution is always x comma y. So now I have the solution to my system for part A. For part B, it looks like it'd be really easy to get y by itself. I can here write that 3x is equal to y if I add a y on both sides. If I know what y equals, then I can substitute this in place of the y in the other equation. So 4x and 3 y's equals 26, but y is 3x's. So I basically made an equation where I know what y equals. This lets me create an equation with only x's. Oh, let's just call that 2. I can do my division appropriately. And then we know what x is. I can now use that to figure out what y is. If 3x equals y, then 3 times 2 equals y, 6 equals y, and then therefore my solution, when I put those together, is parentheses 2 comma 6. I write my answer as an x comma y. This is how we solve systems of equations using substitution. And like I said, we might have some special cases here or there where maybe we end up with an actual independent situation where we solve for both variables. We find our solution is an x comma y. Other times it may not work out quite so well. Here it's really easy to get y by itself. Y is equal to 3x minus 1. I'm going to put that in place of the y. So 9x minus 3y equals 3. And so I know that y is 3x's minus 1. This gives me 9x's minus 9x's plus 3 equals 3. So I get 3 equals 3, right? Because those sum to 0. And so this is true, which means that this has infinitely many solutions. And it means that this is a dependent system. Sorry for my handwriting. All right? On this side, it'd be really easy to get y by itself. All right? So y is equal to 3x and 6. I'm going to plug that expression in for the y value in this second equation. And so let's put that expression in, and then let's do our algebra 1. Oops, minus 12. And so I end up with negative 12 equals 25. This is false, so this is inconsistent because there are no solutions. All right, and so that again references that bottom of that table. If we have a true statement, it's dependent. If we have a false statement, it's inconsistent. So this is how we solve using substitution. You got to see 4 examples of that. How many more examples do you want? Come get them during the seminar. All right, go look on YouTube and type in solving systems by substitution, and you'll find 1,000 more examples. Solving by elimination is, again, a little more complicated. You have to be a little more thoughtful. You have to think about least common multiples of coefficients. But we're going to multiply one or both equations to make opposite coefficients for one of our variables. And in doing so, we will add to eliminate one of those variables. That gives us an equation where we can solve for the other variable, get us a numerical answer that we then plug back in just like we did at the end of substitution. So here I already have opposite coefficients. These are opposites, positive 3 and negative 3 for my x's. And I can literally just add these together. This makes 0 x's, this makes negative 1y, and this makes 3. So the opposite of y is 3. That means that y is equal to negative 3. Once I know what y is, I can put that anywhere I want, either here or there. All right, I'm just going to keep things positive here. I'm going to add the negative 3 to get my negative 9, which means if I have 3x minus 3 equals negative 9, I'm going to add 3 on both sides to get negative 6 and divide both sides by 3 to get negative 2. So that means I have the x comma y, negative 2, negative 3 as my solution. We can get these, but we need to write the answer as our x comma y because that's how we solve a system of equations. Now these, I don't have any opposites. I could choose to eliminate x's or I could choose to eliminate y's. For clarity's sake, I know that the least common multiple here is 6. I can multiply this equation by 3, both sides of the equation. I can multiply this equation, both sides of the equation, by 2. And that would give me, let's do negative 2, so that we can distribute and make opposite coefficients for the x's like I had over here. This is going to give me positive 6x and a positive, 12y and a negative 12. I'm going to get a negative 6x and a negative 10y and a positive 6. I don't have to write the plus for positive there. And then I add these equations vertically. These sum to 0. That's the point. That's why I multiply by these numbers so that I can eliminate these values. But when I add these, I get 2y's. When I add those, I get negative 6. And so I can solve to find out that y is equal to negative 3. See how fantastic that is? So once we know what y is, I can use either equation. All right, over there I use the top equation. Over here I'll use the bottom equation. It's really a who cares. As long as you pick one of those equations and you write it correctly, then I'm assuming that you will do your Algebra 1 correctly. Sometimes it doesn't work out that way. Here's negative 15. I'm going to add 15 to both sides. It's going to give me 12, and so x is equal to 4. All right, so now I know my x, comma, y as my solution. Okay, so this is how we solve by using elimination. Obviously, you've done this in Algebra 1. You spent weeks on it in Algebra 1, but it's been a couple of years since Algebra 1, so I want to make sure that we are covering your bases. Now, let's see if we have any weird situations where we have any dependent or inconsistent systems as we do elimination over here. In this case here, I've got some x's that don't match up, so I'm going to do the same thing. I'm going to multiply this by negative 3, I'm going to multiply this by positive 2. When I do that, it's going to give me now a situation where I have positive 6x's, a negative 12y, and a negative 18. When I double this one, I get negative 6x's and positive 12 and a positive 16. Now when I add these, you're going to notice that I have opposite coefficients for my x's and my y's. So I get 0 on the left, and I get negative 2. Well, this is false. The system is inconsistent, and therefore there are no solutions, all right? And so all of that stuff needs to be thought and written and communicated so that you are communicating to me what it is that you know and have learned. I'm going to subtract 3x's from both sides in that first equation. Now I have this system here. So forgive me if I'm still leaving this equation, I'm just subtracting 3x's, so it goes in this standard form of a linear equation. So now I got the x's lined up, got the y's lined up, I got the constants lined up. I'm going to multiply the bottom equation by 2, so that I keep the first equation same. I didn't have to multiply that. Isn't that nice? Yay! Multiply the bottom equation, I get negative 6x, I get a positive 10y, and I get a positive 12. You can tell that these are going to add up to, say, 0 equals 0. This is true, so this is dependent, and there are infinitely many solutions. All right, so sorry I had to do like 4 examples of each type, but it kind of showed you an example, 2 examples of independent systems, and then an example each for inconsistent and dependent systems. Now, where we're going to take this also, besides practicing the basics here, is I'm going to encourage you to think about how to apply that in terms of these real-world problems that we may encounter and need to solve. Now, this is kind of your classic, math class, like, why do you have this much fruit? Like, why is someone walking through the store with 100 watermelons? Kind of the same idea, but you can kind of think of ways in which we can break down and use math to sort of explain cost analysis, right? And these are things that can kind of help you articulate kind of the results of a real-world encounter with math. And so it says you're buying apples and oranges for your soccer team. You need 24 pieces of fruit. It doesn't matter what is what. Apples are 50 cents each. Oranges are 30 cents each. How many of each? If you want to spend exactly $10, all right? Let's pretend that sales tax is included. You're at the farmer's market. They're just like, this is how much it costs you. So how many of each? So this sentence right here is a question, so there should be a question mark, dude, is what defines our variables, all right? So x is going to be not apples. X is going to be the number of apples. Y is not going to be oranges. It's going to be the number of oranges, all right? And that's really important that you can distinguish that, because we're not solving for apples, right? Apples are apples. We're trying to find out how many apples, right? So we're trying to find the quantity of apples and the quantity of oranges. This is a situation where when we write our system of equations, or when we solve our system of equations, our answer isn't going to be like x comma y, but I'm going to use the letters x and y, because that might be a little bit helpful. So we know that apples cost 50 cents each, and we know that oranges cost 30 cents each, and we know that the total is $10, so is what we can spend. We also know that the number of apples and the number of oranges has to equal how many? How many pieces of fruit do I need? Well, I need a total of 24. So I'm not going to solve these systems, but what I'm going to do is I'm going to practice writing the equations. My first equation is a quantity equation, that the number of apples and the number of oranges has to be 24. Now, each of these apples cost 50 cents. So if I bought, let's pretend I bought 10 apples. How much is that going to cost? Well, 50 cents times 10 apples is going to be $5, right? Well, how did we do that? Well, we used multiplication. I took 50 cents, all right, and I multiplied it by the number of apples that I bought. All right? And the same with the oranges. If I bought 14 oranges, how much would that cost? Well, 14 times 30 cents each, how much is that going to cost me? So I know that I would take 30 cents times y. And so the cost of how much money I spent on apples and the cost of how much money I spent on oranges is going to equal the total amount of money that I spent. So here we have two equations that now we can use to solve our system. We can solve by elimination, we can solve by substitution. The method that you choose doesn't actually matter to me. What matters is, can you read these sentences and then create math sentences, create equations that model this situation, right? And that's tricky because one, it requires that you read, and two, it requires that you understand what's happening mathematically. Now, the way I hope that I talked about that, like how many pieces of fruit? Well, if you've got so many apples and so many oranges, that tells you how much fruit you have, right? That's addition. So hopefully you can kind of connect some of those dots. Let's try this one. You and a friend go to Taco Bell for lunch, you order 3 soft tacos and 3 burritos, and that's how much you cost, or you spent. Your friend spent only this much, but they had 4 soft tacos and 2 burritos. How much do the soft tacos cost? Ooh, this is a how much question. All right, so this is going to be your x value, and this is going to be your y value. X equals cost of the soft tacos, whereas y is the cost of the burritos. All right, so we know we've defined our variables, and it's a dollar amount. All right, so we know that for me, or you, whoever this is, all right, that we took 3 soft tacos. So how much did we spend on soft tacos? Well, I took 3 of them times however much they cost. And then we had 3 burritos times however much burritos cost, and that cost me $11.25. Likewise, your friend had how many soft tacos and how many burritos to spend their $10. This is your system of equations, and you can solve those systems of equations using substitution or elimination or whatever else. But here it's different than just a sum equation and a cost equation. Here, well, I bought this quantity and it cost me that much. They bought that quantity, it cost them that much. So this can help you solve for x and solve for y to say that, oh, x is, here's how much soft tacos cost. They cost $1.25 or whatever the total ends up being. I haven't solved these. Let's see if you can create equations for these. You do not need to solve them. What I would like you to do for these situations is you make the equations, you make the system. And that is how you're going to finish your assignment. Get that done. Upload your answers through letter D of example 3. Once you've done that, you can likely say that you have a variety of tools to solve a system of equations.